Some of you had the wrong answer, so here's a review. First thing you must do is go inside the parentheses and do multiplication first. So that's 10 and then 9. 10 minus 9 is 1. Squared is 1 times 4 is 4. 9 plus 4 minus 3 would be 10. Some of you missed this one, so we will review it. Inside the brackets, you must go inside the parentheses. So 6 minus 4 is 2. Squared is 4 times 2 is 8. Plus 3 is 11. Minus 5 is 6. Times 4 is 24. Plus 5 is 29. Minus 2 is 27. We had some wrong answers on this one, so we'll go back and look at it.
I don't know what I did wrong.
You must start inside the parentheses. In this case, you get 7 minus 3 is 4. 4 squared is 16, not 8. And then times 3 is 48. So hold that. Then go back to this parenthesis here and do 8 minus 5 is 3. Squared is 9. Times 4 is 36. Now add the 48 and 36 to get 84, subtract 3, and you get 81. Pick a number from 1 to 5. The winning number today is 4. Your homework after the pretest, bring that up. We have 22 here and 21 with homework, so 21 divided by 22 is 95. The answers are coming up. They're all on one screen, so check to see how many you had right. Remember, this is a pre-algebra final exam review, so it's from stuff you did last year. That's why I gave it to you. Pre-test results. We'll go through each class. First period, the high score was Johnson. And for first period, the high score was 46. So that means they know 46% of the course before we go through it. That's really good. And for the rest of first period, we have the following. These people get a homework pass in addition to Salyers. He tied for the bottom of the 4 scores, but I didn't put his name on there. Johnson, Darnell, Bartley, and Ruark. For fourth period, Kleiber had the high score, and that score was 36. And here are the top 10: Kleiber, Bruton, Clark, Owen, Stickler, Webb, Hellier, Kegley, Imes, and Hamilton. Fifth period, it was Baldridge with the high score, and the high score in this class was 46. We have 11 people because at the bottom end of the top 10 we had a tie score. So Baldridge, Blizzard, Boyd, Armstrong, Hammond, Bailey, Perry, Montavon, Garrett, Carver, and Blevins, D. Today's objective, you have a brand new one. The objective today is to create equations and inequalities in one variable and use them to solve problems. Here's example 1. There are 60 students going on a field trip. Mrs. Hickman's class has 17 students and Mrs. Bentley's class has 25 students. What equation, not the answer to the problem, but what equation can we create to solve for the number of students in Mr. Royce's class who is also going on the trip? Yes?
You add 25 and 17, and then you get that answer, and then you subtract that answer by 60.
So we'll need 60 and then minus this, and then what? Remember, we have to have an equation. It has to have an equal sign, and what's it equal to? X, yes. So I need to rewrite this so it looks a little neater. You're going to have 60 minus the quantity of 25 plus 17, close the quantity, and all of that equal to x. You could have also had this, x plus 17 plus 25 equals 60. There's more than one right answer for an equation you could set up for these problems. Example 2. There are 115 students from 3 classes that will eat in the cafeteria today. Class 1 has 43 students. We do not know the number of students in Class 2, but it has half as many students as Class 3. What equation can we create to represent the number of students in Class 2? How many different items am I going to add together to get 115? 3 items. So here's 1, 2, 3. I have 3 classes, and the total is 115. This is Class 1, Class 2, and Class 3. What do I know about Class 1? It has 43 students. Do we know what Class 2 is? What can we let represent Class 2? X. But Class 2 has half as many students as Class 3. So what could we say about Class 3 in comparison to Class 2? Yes.
Half X.
Half X? If X is Class 2 and Class 3 has twice as many as Class 2, then what would I be doing to this to get to Class 3? Multiplying by 2. You are right. Now, if I were going back from this direction, if I went from Class 3 to Class 2, then Carver would be right. You would have to go half. But in this case, we don't know Class 2, but we do know something about it in relation to Class 3. So you have to do double Class 2 to get Class 3. It does say half as many students as Class 3, so that means this is double. That would be right. This equation is right. 43 plus x plus 2x equals 115. Or you could do this. What is 1x plus 2x? 3x. So you could write 43 plus 3x equals 115. You could also put 3x plus 43 equals 115. The question is, how does this help define Class 2? Well, let's say we solve this equation here, and we come up with a value for x. X represents what? Class 2. So if we solve for x, we get Class 2, but what if we wanted to find Class 3? Multiply by 2, whatever we get. And of course, we already know Class 1. There are 3 buckets that contain apples. Bucket 1 is unknown, but we do know that bucket 2 has twice as many apples as bucket 1. And bucket 3 has twice as many apples as bucket 2. If there are 70 apples in all, then what equation can we create to represent the number of apples in each bucket added together? There are 3 buckets that contain apples, and later on in the problem you know that there are 70 altogether. So what operation is taking place throughout these 3 buckets? Yep. Adding, yeah. So we have bucket 1 plus bucket 2 plus bucket 3, and all of that equals 70. So this is 1, 2, and 3. Bucket 1 is unknown, so we make that x. We do know that bucket 2 has twice as many apples as bucket 1. So what do I put here? 2x, yes. And then in the next spot, which is likely where most people made a mistake, if they did, bucket 3 has twice as many apples as bucket 2. So what goes here? 4x is right, yes, because you have to double this here. If you double that, then it becomes 4x. You can also write 7x equals 70 because 1x and 2x is 3x plus 4x is 7x. A class of 30 students is going on a field trip. There are twice as many boys as there are girls. What equation would let us represent this scenario? A class of 30 students is going on a trip. There are twice as many boys as there are girls. What equation would let us represent this scenario? We are adding boys and girls together. Here is a tip or an indicator you can use in the future that will help you out tremendously. There are twice as many boys as there are girls. As there are girls implies that girls is going to be the variable you start with. So if we have boys and girls, there are girls. And boys are what in relation to girls? Twice as many. So you could have 2x. You can use any letter you want. You don't have to use x. I'll take this, or you could have 3x equals 30. The only other possibility is x plus 2x equals 30. Example 3. A group of 76 people are going to tour a factory. No more than 20 are allowed to tour the factory at any one time. What inequality would best represent the number of groups that would have to be formed? Inequality means you must have this, 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 or this in your expression. Okay, so we have 76 people and only 20 can go at a time. What operation would I do to figure out the number of groups I would need? Yeah. Divide what?
76 by 20.
I would do 76 by 20. That's right. And when you divide 76 by 20, it comes out to be 3.8. But 3.8 is not what we're looking for. We're looking for an inequality that represents the number of groups. 3.8 is in terms of groups, but we would put G, for example, for groups. Now, to determine this, we would have to look at the 3.8. The 3.8 comes from 76 divided by 20. If I need 3.8 groups, can I have 0.8 of a group? No, you've got to either have 1 group, 2 groups, 3 groups, or 4 groups, or 5. How many groups are needed? And Carver is right, it is 4. You would need 4 groups, but we don't put that in the inequality. If I need 4 groups, then would G have to be less than this amount? Would it have to be greater than this amount? Greater than or equal to, or less than or equal to this amount? Yeah. G would have to be less than or equal to? Does anybody agree or disagree? Just think of 3.8 being right here just for a moment. Would my number of groups have to be greater than 3.8? Yes. What if it ended up being right on a number? For example, let's say we divided this and it did end up being 4. Would the number of groups I need have to be greater than 4? No, it'd have to be right on it. So it's not just greater than, it's also equal to. So he was right. Greater than or equal to. That's the same thing as saying G is less than or equal to 76 over 20. It depends on where the inequality sign is pointing. If you read it from right to left, Baldridge is right. G is less than or equal to 76 over 20. But if you read it from left to right, 76 over 20 is greater than or equal to G. Just depends on where it's pointing. Both are right. On your homework, these are the exact same examples and practice problems that are contained in my lesson for today. And we just finished with number 5, which was example 3. What you need to do on these problems is not only go back and rewrite the equation or inequality, you must also find the exact answers for each one.